to use a full sheet of paper. So, well, because the final is cumulative, so 2 note cards together equals a full sheet of paper. And then I don't have to buy a bunch of note cards.
That's like my regular note card.
Sweetheart, I'm so sorry.
Except I still forget stuff.
The idea is the note card's not going to save you if you don't know it.
Yeah.
So that's why I don't worry about it. The note card's just there to honestly reduce test anxiety. Here you go. All right. Ooh, that's so loud. If only I could change the volume. At least this works. I cannot change the volume of this either, so I will just talk at a reasonable volume. I'm fairly confident everyone knows this, but just make sure. The test is coming class. It's coming Tuesday. Yeah, I know, right? So it'll be on momentum, energy. So I'll just list the titles: work and kinetic energy, conservation of energy and potential energy, momentum, conservation momentum, and then universal gravity and center mass. So make sure you do all those things. And like last time, you all have a quiz on center of mass that opened yesterday. The quiz will be due this coming Wednesday. The quiz is due after the test. Do not wait till after the test to do the quiz. It's silly. Again, think of the logic. You can either learn that you don't know it on a quiz, in which case you get a second attempt and you get to improve and that. Or you can learn you don't know it on the test, and it is what it is, and it's worth a lot more points than it stakes. So the point of the quiz is to see if you know it. That's why I have made those assignments. They're little like checks. They're not perfect checks, but they're better than nothing.
For the final exam, can we just take 3 of these together?
Can you tape 3 of them? It'll be 2 of them.
Oh.
Yeah. So the final will be effectively 2 note cards. A piece of paper is 8.5 by 11. So a 5 by 8 note card, 2 of them equals basically a full sheet. So you could tape 2 note cards together, which is valid. If you're like, man, I really, really love my note cards that I've been using up to this point and I want to reuse them, take a picture, crop the picture, paste it in a Word document, and then just print it and staple it / glue it to the sheet of board. Just print the paper. Yeah.
Does that mean you can do double-sided with one note card?
Yeah.
Yeah.
Well, no, they get to do both sides of a note card anyway.
Oh, okay.
That's been a thing. All right. So again, sadly, there is no way, and the system is down. IT difficult. This will happen to you at some point in your life. Technology is a wonderful thing, but like anything in life, things sometimes don't work. Sometimes humans don't work. So anywho, here we are with no projectors. So I will have it on the stream. So if you're like, you still want to see what's on my laptop, otherwise I'm just going to talk through it as best I can. But if you want to see what's on my screen, I even tried to check. I was like, maybe I can log into this computer and then like send it to all your computers. Nope, I can't log into this because the domain's down. So I have explored all possible options.
Oh, come on.
Yeah. So you can open up the slides on your computer. Remember, the exact same slides I'm going through have already been posted. So you got the stream. You can stream. You can open up the slides. Like there is options to still see the content that I'm presenting. Anyway, joke of the day.
Okay.
Good morning. It's very
The
loud.
joke today is, why does Humpty Dumpty love autumn? Because he had a great fall. It's the only one I could find.
Yeah. That's a classic. Okay. So, and you know what? Maybe I'll have my handy assistants. Do you want to write equations on the various boards?
Oh, yeah.
Okay, so let's just kind of talk through what's there, and then they'll get jotted down on various whiteboards. I don't know. We'll figure that out. You all can... All right, I'm going to delete all ink in the presentation because I'm going to do my own ink. Goodbye, ink. Okay. Let's make this a full screen. The first thing we learned after test 1 was about work. Now, so the first thing we started with was work, and work was how much energy you gain or lose. And every other form of energy was derived from work. So we use the work equation. The work equation is work equals the integral of F dot dr. And that was like the first time you all had probably seen a dot product before. I don't know, maybe not, maybe you've seen it before. And I told you all a dot product is just the same thing as the magnitude of F times the magnitude of the direction you're going times the cosine of the angle. And if you all remember, all that's doing is finding the part of F that lines up with dr. You're just finding the part of F that lines up with dr. That's the whole point of this. And you're multiplying those two together. And the logic is, if I push something in the direction you're going, you gain energy. If I push something opposite the direction you're going, you lose energy. Like, that's the logic here. Now, I'll tell you all, this equation, I tried to figure out where it was derived from, and it is a messy rabbit hole. Like, where did this equation come from? Because remember, everything in physics, it wasn't just written on a wall somewhere and someone found it and said, there it is. It's a messy history where basically people talked about energy and they actually came up with the equations for energy and then they found this from those. So it's a weird, long system. Because remember, y'all, energy is a made-up thing. Energy is just something that they found that when you calculate it and then stuff happens and then you calculate it again, the numbers are the same. That's energy. It's weird. Yeah. And if the force is constant, you can pull it out of the integral. In which case the integral turns into FD cosine theta, where D is how far you've gone. And then we said kinetic energy is 1/2 mv squared. We derived it. Feel free to check it out. The faster you go, the more you have. And there was the whole work equals change in kinetic energy if there's no other types. But really don't worry about that one. I'm going to go ahead and remind you all right now before I get any further. The magic sauce is energy initial plus work equals energy final. And there's 3 types of energy. What are they? Kinetic. What else? Kinetic, potential. What kind of potential? Cool. And what's the third one? Elastic. Now, there is more than that. There is way more than that. But in our class, those are the only 3 terms that get chucked into the E. Everything else goes with work. If there's heat loss to thermal energy, work. If there's heat loss to friction, work. Work because someone's pushing an object and making it go faster, that's work done. If someone's like pushing something. Everything else goes into work except kinetic energy, potential due to gravity, potential due to springs. All right, which is a nice segue to the next slide, which basically says the same thing. Energy, start with the energy you end with unless someone adds or takes away energy. Someone does work. I really, really hope that a lot of you, that makes sense to a lot of you, because when I took this class, work was just something that I kept saying and I didn't know what it meant and it was nonsense. So I hope the idea that work is just whether you gain or lose energy. That's all it is. If you add work, you're gaining energy. If work is negative, you're taking away energy. That's work. It's a very weird word that's used in a weird way. But it's there. All right. And what's the unit for energy? It's named after one of the guys that came up with it. Joules. Good thing to remember somewhere in your head. Don't forget your units. You need to know what the name of them are, so when you're reading a question, if you see joules, you know what it is. And then there's power, which is the work done per time. So you just take how much energy is added or taken away, and you divide it by how long that takes, and that's how much is output. What's the unit for power? Watts. Yeah. Really, really, really straightforward. Conservation of energy. Once you've done a few problems with them, life is good. Like, that is the magic sauce. Once you've just done a few problems, if you haven't done them already, we're running out of time. But energy really is just one of those. If you just do a few problems, you'll see it's very straightforward. Okay, that's energy. We'll do some problems with those today. I'm just doing a quick overview of all the topics, just kind of a refresher. And then we will literally just spend the rest of class doing random clicker questions and random made-up problems that I make up. That'll be good for us. All right. Momentum, another made-up, kind of semi-made-up thing. Momentum is another one of those things that they just kind of said exists, and then they found that if you calculate it in the beginning, and you calculate at the end, it's the same. And it's great. And it's super, super, super convenient because any collision ever, the only requirement to use conservation momentum is that no work is being done in the system. That's pretty much the only requirement. The only requirement is that no work is being done. No forces are acting on it in the direction of motion. As long as that's the case, conservation momentum works. So every single collision you all see happen, conservation momentum basically can use as long as there's no, and I guess the other way to phrase this, there's no non-conservative force, no, even conservative forces, you don't want acting on it. As long as there's no external forces, as long as all the forces can be accounted for in the system. For example, two cars colliding against each other. Yes, there is forces involved, but it's all in the cars that are actually hitting each other. So it's fine. Whereas if you have a case where, I guess the mic's you cannot use conservation momentum. If I like drop an object and then I have it hit something on the way down, you cannot use conservation momentum with that problem. Because let's just prove it really quickly. What's the momentum of this eraser? 0. What's the momentum when it's falling? Not 0. Are those equal to each other? No, look, you can't use conservation momentum. Ta-da! We proved that if there's an external force, you can't do it. I say that. You can if you set it equal to the impulse, but I didn't teach you all that. So for our cases, if there's an external force, we're not going to bother with it. And it's a vector, so you have to break into x and y. Don't forget that. Okay. If a problem involves collisions, you are almost guaranteed to use conservation momentum. And within conservation momentum is an equation as well that I want to remind you all that the impulse, the force times the change in time equals the change in momentum. So if there's a collision, you basically have the change in momentum either will equal each other, but if there's forces involved, you can find the forces with that equation. Force times change in time equals change in momentum. All right, and then last two things. We're just kind of zooming through this because I can't. Normally I'd spend more time on these slides and I give you all hypothetical situations that I draw on here, but I can't show you them, so it's not very useful. So that's why I'm just kind of jabbering on, and then we'll get to some problems that I'll write somewhere that I can send to you all so you can actually see them. Yeah, there's the impulses on the next slide. Ran out of room. Units for momentum are funky, but they come from the math. Kilograms times meters divided by seconds. Mass times velocity. You can just derive the units if you forget them. Mass times velocity. What's the unit for mass? Kilogram. What's the unit for velocity? Meters per second. You did it. Multiply them together. Okay. Universal gravity. If I get infinitely far away from the Earth, what's the force due to gravity? How much is the Earth affecting you? Yeah, it's 0. If you're infinitely far from the Earth, can you tell that the Earth exists? No. Can you all tell that all the other planets out there in the universe, can you all see a planet infinitely far away? Are you being affected by it? No. So clearly, G does not equal 9.8 everywhere. Like, really simple logical step there. You get farther away, and the force of gravity is going to decrease. And Isaac Newton discovered that, and he made the equation. It is capital G M1 times M2 divided by R squared. M is one of the objects. M1 is one object. M2 is another object. R is the distance between the centers of those objects. R is the distance between the center of those objects. And if you say it's the distance to the surface, case in point, roughly how far away am I from the surface of the Earth? If I went and stood on the grass outside, roughly how far away am I from the center of the Earth, from the surface of the Earth, the surface of it, if I go stand on the grass outside? 0. What happens if you divide by 0? Yeah, you get an infinite force. When you all go stand on the grass, do you experience an infinite force? No, not a trick question. So, that's a reminder to you, if you're ever like thinking about, is it from the center or the surface? Just ask yourself, what if it was the surface? And you get an infinite force, and that's nonsense. That's the nice thing with physics. If you're ever uncertain on something, you can just think through like other things that you do know and try to come up with a solution. We call these boundary conditions. We call these kind of the extreme cases. Take an extreme case and see what happens. Does it match your logic? We're usually pretty good at figuring out extreme cases. I've been doing it this whole time. What's the force of gravity infinitely far from the Earth? 0. Like, those are those extreme cases, and they let you check your logic. If your logic does not work for the extreme case, it definitely doesn't work for the normal case. It's a really, really useful way of thinking that applies far beyond this class. That applies to like anything you all do in life. If you're uncertain on the logic of something, take an extreme case and test your logic. So, anyway, all right. Newton's second law says F equals ma. If there's one equation that I hope you all remember from my class, it's that one. In my mind, F equals ma is like mitochondria is the powerhouse of the cell for physics. Like if you don't know F equals ma after my physics class, I failed you, or you failed me. I don't know. I don't know which way it goes. I mean, gosh, we use it so much. If you don't know by the end of my class, I don't know what to do. Why is this important? If the gravitational force is g m1 m2 over r squared, how do I turn that into acceleration if F equals ma? Yeah, they're both force, right? Set them equal to each other. What happens to one of the m's? It cancels out. Ta-da, you derive the acceleration equation. The acceleration equation, I do not believe, is on your formula sheet. So that is something you can either add it to your note card. If you want the acceleration due to gravity, for example, on the moon, or on Mars, or literally anywhere, or even on Earth, 300 meters above the Earth's surface, you have to kind of derive, because it's F equals ma, whatever. And you can put on your note card if you really want to. So great, get rid of an m. What path do most celestial bodies take around when they orbit? A circle. If you ever hear the word circle, what equation should be, what concept should be like triggered in the back of your mind somewhere? Centripetal force. If you all ever see circle, you may not use centripetal force, but that should be like a trigger in the back of your mind, just like, okay, that might be a thing. That might be a useful thing. If something is going in a circle, centripetal force should kind of like a little tiny little light bulb should kind of ping on. You might not use it, but it's really common that we use it when things go in a circle. And so when things go in a circle, the Earth going around the sun, what's the, let's pretend like all the other planets don't exist. What's the only force acting on, actually what is the only force acting on the Earth? Gravity. And I don't even have to make the argument that like ignore all the other planets. It is literally gravity due to every other planet. But what's the only one really affecting the Earth in a significant way? The sun. So Earth is making a circle. So mv squared over r, you get centripetal force equals the only force acting on it in that circle, which is g m1 m2 over r squared. That is a trick. That is a very helpful trick. Do not forget that if things go in a circle, you can set mv squared over r equal to the forces pointed inwards or outwards, the components of forces that point inwards or outwards. It is a very, very, very useful trick that we have used many times in this class and we'll continue to use. This is not an equation on your... Centripetal force is on your formula sheet. Nowhere on your formula sheet does it say mv squared equals g m1 m2 over r squared. Because that is an equation that you build based upon your problem. It is not always equal to that. It only is equal to that in the case of gravity being the only force acting on it. All right. Great. And that lets you do things. And we will do things with that today. And the last equation was the universal gravitational potential energy. So if you take the integral of force times distance, you get potential energy. You get the work done, which is potential energy. If you integrate that force with respect to r, and there's a typo on my slide because I forgot to do this. I gotta fix that. If you integrate that, you all did it before, you get g m1 m2 over r. You drop an r squared and it becomes negative. And it becomes negative. So the universal gravity equation, the universal gravitational potential energy equation, negative g m1 m2 over r. What's the largest value that can reach? What is the largest value that that potential energy can reach? It's 0. 0 is the largest value that equation can reach because every other number is a negative. -1 is smaller than 0. -2 is smaller than 0. -3 is smaller than 0. -1,000,000 is smaller than 0. That equation, the largest value it can reach is 0. It will never be positive. You can't have an r that's negative because that equation doesn't work when you're inside the surface of, well, r is the distance from the center of the object. You can't get a negative distance from the center of an object in the radial direction. R is impossible to be negative.
G will be given as a.
G will 100% be given. Yeah, if you all look at the formula sheet, it's at the bottom. 6.674 times 10 to the minus 11. One of those numbers that I have memorized now, but ask me in 2 months and we'll see. No, 2 months, maybe, give me 3 months. No, I'll be teaching the class next semester. I don't know. If I didn't teach this class for like a couple months, it'd be gone out of my head. My memory stinks. Physics isn't about memory.
Is the potential energy expected gravity, is it always negative?
Yes. Yeah, that's a great question. Is it always negative? Yeah. Yeah, that's a good point, and that's because I forgot to put it there. And someone pointed out yesterday, and I need to make a note of that to remind you all because I printed the test about the negative. Gosh. I'm going to make a reminder in my calendar to tell you all on the test that it is a negative. Because I do not want to forget. Remind, potential, energy, negative. Okay. All right, and that's universal gravity. And we did a problem with universal gravity where we found the escape velocity, which is a really cool problem, how fast you need to go so that you will never go back to the Earth ever. And it was just a conservation of energy problem. We started with the potential energy of being on the Earth's surface. We started with some initial velocity. What is your final energy if you are infinitely far from the Earth and you're not moving? How much energy do you have if you're infinitely far away from the Earth and you're not moving? It's 0. That's how we did escape velocity, y'all. If you are infinitely far from the Earth, the potential energy goes to 0. If you're not moving, kinetic energy goes to 0. So we set up a conservation of energy problem where we started with some kinetic and we started with some potential, and at the end it equals 0. And if you're like, how did that work? Remember the potential energy one is negative. So kinetic energy is positive. You add a negative, it's possible to get 0. Energy is all relative. You don't really care how much energy you have. You just care how much your energy changes. All right. And then the last thing we finished up this last class was center of mass. Center of mass was 1 over, add up all your masses, 1 divided by all your masses added together, times each mass times where it's located. And you add all those terms up. And we practice that in X and Y are separate. I know we just finished center of mass, but do not neglect to practice those problems. There will be problems on the test related to center of mass. Just because I only covered it this last Tuesday, it will still show up on the test. Don't, at least try a couple problems. At least look through those things. I know it's a tendency to only focus on the things that happened previously and the ones in the end get neglected. Even if you only spend 10 minutes looking at it, it's better than 0 minutes. If you neglect them entirely, it will not go well for you. There's a diminishing returns when it comes to studying, where the initial minutes that you spend have a huge gain, and then after that, you get kind of a diminishing returns in how your time is invested. So the first, even just spending 10 to 30 minutes on a topic has huge, will drastically increase your performance on whatever that topic is. If you haven't experienced that yet, you will. If you go into a test without looking at anything, you do absolutely crap. If you go into, you may or may not do absolute crap. If you spend even just 30 minutes reviewing something, now 30 minutes isn't enough, but it's better than 0, you will find that you do way better than if you looked at nothing. It's just one of those, you'll find that out for yourself. That's true of anything you do in life. If you have a presentation that you have to give, you work for some company and you're about to present to some people, If you just spend 5 to 10 minutes before the presentation practicing it, looking over your slides, it will go way better for you. It may not go ideal because 5 to 10 minutes isn't probably enough to prepare for these things, but it'll go way better than if you do nothing. You will see that for yourself as life goes on. You get a huge gain from just a few minutes spent on something. And then if you spend like hours upon hours, at some point you get diminishing returns. So, and this is of course assuming you're studying correctly. There's the phrase, practice makes perfect. Totally false. Practice makes permanent. Whatever you're practicing becomes permanent. If you practice wrong, you just get it permanently wrong way. So that is the better phrase. I forgot who told me that at some point. I was like, that's a really good point. So you do need to make certain you practice well, and of course practice the right things. That's obvious, but it's worth mentioning. Okay, last thing with center of mass, if you have a continuous object, I told you all you could use the density function for it, and then you integrate it. And what's really cool about this is you all actually saw this on your recitation. Oh, you don't have recitations. That's that. Okay, my other class, they have like the separate problem solving sessions, and they got a function that wasn't of density, but it was like the height of the object. And so the equation I gave you all was 1 over the rho dx. So basically that just gives you the sum of the mass. So 1 over the integral of rho dx times x rho dx, and the integral of that one is how you get the center of mass for a continuous object with a varying density. But what's really cool about this is this density function, you could just replace that with the height of the object. Because if remember that triangle? If a triangle is really tall at one spot and it gets really narrow at some point, that's analogous to how the mass is distributed. I.e., it's analogous to the density. So for example, if I gave you all a triangle, you'd solve this problem the exact same way, except instead of a density function, you'd put the slope of a triangle. You put y equals mx plus b for your density function. I need to give one like that in the future because it's cool to see that connection. But there you go. All right. That's an overview of the entire things we've covered in the last 4 weeks in 30 minutes. Well, less than 30 minutes. Now we're just going to practice those things. So I'm just going to kind of throw out random. I actually probably will do the nice with clicker questions that they get sent to your device so you can see them. But they will not be graded. They're not going to count towards your grade. After today's class, I'll somehow, some way make them not count towards your grade. I won't want to delete them in case you want to. Well, they'll be on the slides. So I'll do clicker questions just to send them to your devices so you can see them because otherwise you can't. So you know what? Let's practice a skill that's the most basic skill. I'm going to give a hypothetical problem. And I'm going to ask you what type of problem it is. Is it an energy problem, a momentum problem, a universal gravity problem, a center of mass problem? Because if you can identify what type of problem it is, it's very likely you're going to get the problem correct. Just being able to identify what type it is immediately vastly increases your probability of getting the right answer and also improves your thing. So, let's see. An asteroid blows up into 5 pieces. Let's give it 3 pieces. 3 pieces. I give you the initial velocity, final velocity, and masses of the 3 pieces. Nope. I give you the initial velocity of the asteroid, final velocity of 2 pieces, and mass of asteroid and 2 pieces. Find the velocity of the 3rd piece. And this is going to be a work, conservation of energy, which is kind of work, momentum, universal gravity. You know what? I'm just going to lump work and conservation of energy together because work and conservation of energy or a center of mass problem. And I am now going to get out my iClicker thing so I can actually I didn't plug it in because I wasn't originally planning on doing this, but here we are. All right, boop, boop, and boop. All right, great. So hopefully you should be able to see it now. I'm gonna check if you see it. Since I'm on. And I can see your responses, so. What do y'all think? Why?
Well, first of all, I literally did that problem. Yeah, but also, it's massive.
Alright, what about y'all? All right, give y'all like 10 more seconds. In 5, 4, 3, 2, 1. All right, they're looking good, y'all. What'd you say? I mean, I know what you said, but like, why momentum? Because it blew up. That's literally it. If you have something that blows up, if you have something that splits into parts, if you have something that starts together and spreads apart, literally the only way you can solve that problem in this class is momentum. I have taught you no other ways. Like, I don't even know where you'd begin. You'd have to know why, like any other way, you'd have to know why it blew up. You'd have to know the force of that explosion. It's probably not a constant force. What's really cool, you don't care why it blew up. You don't care if the pieces left at different times. You don't care if one part blew up and then another part broke off at a separate time. You don't care if the force was constant. Like, all these things you don't care about with momentum, and it just works. Super, super cool. All right, great. Another problem. Let's see here. Angelina, give me a planet and a moon. Titan has the moon. Darn it. Jupiter?
I'm like doubting myself.
No! What is Saturn? All right. Saturn has a moon, Titan, which orbits it. I give the time for one revolution of Titan, and I give the distance of Titan from the center of Saturn. How do I find the mass of Saturn? And then I copy my possible answers. And as you're doing this, if you know what the topic is, go one step further. What equation would you use? Go one step further. If you're like, great, this is obvious. I know what topic it is. Great. What equation are you going to use to solve it once you've identified that? Given what I've given you in this problem. So I give you the time it takes for one orbit. I give you The distance of Titan from the center of Saturn. This is a great way to study. Look at a problem. What type of problem is it? And immediately can you jump to what equation? Can you kind of skip steps 1 and 2? Steps 1 and 2 are to help you if you get stumped. But if you get really good at physics, you can skip steps 1 and 2 and identify step 3 from the get-go. You still need to write down your givens and missings because it's going to help you. But.
Yeah,
Are all the physics classes like? How are those looking at this point? Are they all full?
I already enrolled like a while back. My enrollment apparently they were waiting.
All of them? Yeah. So
I'm
we got crazy enrollment in part this semester, like 1,000. Well, so it's fine to admit people as long as they communicate that to UCF. But no, as long as they communicate that to the department, they need to have enough professors to teach the class. I'm happy. The more people they admit, the more job security I have. But we just need to have communication channels that say, "Oh, we need assistant professors to cover that." Yeah. They pretty much are always incentivized to add more, so they're always going to try to. I don't know when they will make this combine, but it is everyone's best interest for them to add more classes. It helps you all graduate in time and manner. It also benefits the student, one of the metrics that we're trying to improve. So the more people that are waitlisted, the more it impacts both you all and the university also. So very, very likely they'll have I oversee which is separate from everything. That's its own thing. All right, let's see how we did. Ooh, we got different answers slightly for this one. All right, so what's the answer? Sorry, I should give you a timer, but it's not working anymore. It's universal gravity. How do you know that? And this one's a little subtle. People are split between universal gravity. I say subtle. This one, some people put universal gravity, some people put center of mass. So how do you decide what topic to use? And it all comes down to what you have. For center of mass, there is literally only one equation for center of mass. You can always quickly check, can I use that equation? And if we look at center of mass, yes, the mass of both planets is in there. But here's the problem. What do we not have? Why can't you use center of mass? What variable do you not know? And the center of mass equation, you don't know specifically the distance from where. So we do have that. That's a good guess. We do have the distance. Where do y'all want to set the origin? Where do y'all want to set the origin? Center of mass, you can set the origin anywhere. Where do y'all want to set it? Choose. Center of Saturn. Let's make that R1. So R1 is 0. What would R2 be in center of mass in this problem? R2 is the distance from where to where? The origin to the center of the moon. Do we have that? Do you all have the distance from Saturn to the center of the moon in this problem? Yeah. So in this problem, it does say you have the distance of Titan from the center of Saturn. The center. It has to be the center. Even for universal gravity, it's the center. What do you not have in that equation? Because on the right side, we have R1, we have R2. Do you all have the mass of Saturn? No, that's what we're solving for. Do you all have the mass of Io or Titan? You don't have the mass of Titan. That's already two unknowns. You can't solve it. There's another thing you don't know in this equation. There's a third. What's the last thing you don't know in the center mass equation? What's the last variable we haven't talked about? Not gravity. Check out the equation. I'm referencing the one that's written kind of back there, but it's also written over there. Just go left to right. Do y'all know the center of mass of the system? You don't know the center of mass of the system. There's 3 unknowns. You can't use it. This is the thought process for choosing equations. Yes, center of mass equation does have the mass of Saturn in the equation, but you don't know enough to use that equation. You don't have the required tools to use it. This is the thought process for choosing any equation. Do I have what I need? All right, universal gravity, people said that one. What equation are you all using to solve this problem? That is the next follow-up question. If you haven't already decided that, spend some time. I give you the distance of Titan from the center of Saturn, and I give you the time it takes for Titan to make 1 full revolution. How the heck would you solve this problem? Deliberate. Figure it out. We know it's universal gravity. Like I'm telling you right now, it's universal gravity. So I've kind of collapsed what equations, but how would you set up this problem? If you can't set it up now, this is a good one for you to learn how to set up before the test. There's actually no work being done. Oh no, because I'm thinking about yeah. Okay, that sounds like there's the work done on this one is zero. Yeah, but I did. Oh, nice. I don't know if y'all have it off. It's a great song. Mainly grab a breakfast. Nice. Okay. We could get lost. Yes, nice. So, what's given in our problem, y'all? What's our givens? If you haven't figured out what equation to use, you're going to have to go through the steps. Y'all tell me what's given. We got distance. What variable are we going to use for this distance? The distance between the centers of 2 objects. R. That just helps if you kind of know. Remember, there's like X, there's Y, there's D, there's R. They all represent distance. And if you don't immediately kind of choose the right variable, you might end up with, it'll make it harder to choose the equation if you're not sure what to do. If you put it down as X, you're not going to find any equation with X in it. And that might confuse you. So, center between objects, you got R. What else you got? You got the time. Fun fact, there is not a single equation up there that has time in it. So what the heck? What? I can solve for velocity. How? 2 pi r over t. Great. Now we've got velocity. Now we've got r. We have v. We have r. We still have t. We can still jot that down. What are we solving for? Mass of Saturn. Let's put ms. Okay. And you look at the equations. Can we use the force equation for this? Can we just say F equals G m1 m2 over r squared and solve it and get what we want? Why? You have two unknowns. If you just do Fg equals G M1 M2 over R squared, you don't know F. Well, I say you don't know F. You don't know F. Can you use the acceleration equation? Acceleration equals G M1 over R squared. Do you know the acceleration? No. Can't use that one as is. Can you all use the universal gravitational energy equation? Universal gravitational energy equals G M1 M2 over R. Do you all know the universal gravitational energy? No. I can't use that one either. Oh no! We've gone through all three equations. So this is where you have to remember in the back of your mind, what shape is this thing making? What? And then that light bulb in the back of your mind says that was always an option. Centripetal force equals what? Equals the force of gravity. So Fc equals Fg. And this is one of those problems. Look at that. You have to build the equation. You have to build the equation, y'all. Anytime circular motion is involved, you have to build that. No one's going to do it for you. It is not going to be one of the ones listed on your formula sheet. And this, being able to build these equations, this is what separates a surface level understanding from an actual more in-depth understanding. If you can only use the equations I give you on the formula sheet, you can't kind of build your own, and this is one of those cases, that's what's going to limit your grade on this test to like a 60 or 70 at the highest. To achieve an A above an 80% on my test, you cannot just only use the equations that are in the formula sheet as is. And especially on this test, you got to build conservation of energy problems. You got to build momentum equations. Like, moving forward, y'all, so like my standard level and honors levels physics class in high school, it was very much a what's given, what's missing, find the equation that checks all the boxes. When you're getting to the level you all are at, you got to start building your own equations based on how complex, the complexity of the system and what's involved and maybe multiple concepts together. Anyway. All right. Let's see. Another problem. I toss a ball off a cliff with height off a cliff with some initial velocity. Find the velocity when it is a certain distance above the ground. I give you the height of the cliff. Actually, you know what? Let me just put numbers here. I toss a ball off a 10-meter high ledge with a velocity of 8 meters per second at an angle of 20 degrees. How fast is it going? Nope, let's change this. How high is the ball when it's going 10 meters per second? All right, which of the following can be used for this? Conservation of energy, momentum, universal gravity, or center of mass? Oh, let's make this interesting. Air resistance takes away 3 joules. Takes away 3 joules. Do I want to put that? Do you all want air resistance, yay or nay? No. All right, fine. We'll get rid of it. And then I'm going to ask it again with air resistance. All right, I toss the ball off a 10-meter high ledge with a velocity of 8 meters per second at an angle of 20 degrees. How high is the ball when it's going 10 meters per second? So right now, you just got to decide what concept is going to help you solve this problem. Will conservation of energy be useful? Will conservation of momentum be useful? Will universal gravity be useful? Will center of mass be useful? You know on this test that it's going to be one of those 4 things. And then once you pick the topic, build the equation.
Number 3.
Okay. Yeah, I didn't need to give you that.
Okay.
Okay. Did you find potential energy? Did you find kinetic energy? Yeah, I should have been master. If it makes you feel better, I will give you the mass, but you don't need it for this problem. You do not need the mass to solve this problem. But if it makes you feel better, the mass is 1 kilogram.
Yo.
Find that? This is where it sounds like after I said, if there was air resistance, it doesn't cancel out, and that's where I was like, I'm kind of glad I didn't do that. If air resistance was there, I would have to use it. Yeah, it'd be impossible. Air resistance. We don't have the equation. If I tell you air resistance and where would that go? Where would that, if it's lost 3 joules of energy, force loss the energy that you do? A lot. The energy that's gained or lost. If losses system is a certain magical phrase that tells you the variable that corresponds to the energy that you do. I'll give you a hint, it's in the energy section. Spend some time. It'll be more meaningful if you all find it yourself versus I just give it to you. Feel free to just Google it.
Using the whole like
Well, now I put it in.
Alright, I think we're looking pretty good here. And again, if you haven't built, I've given you a bunch of time. If you haven't built the equation, we're just going to build it now. Alright, what's the magic equation, y'all? How are we going to build this? What's the bread and butter of all conservation of energy problems? Energy initial plus work equals energy final. So let's go through that. What energy do you all start with in this problem? Potential. What's the equation for it? MGH. Now, I'm going to start to actually use, instead of H, on the formula sheet it says H, I'm going to start to use Y, because I like Y better. H confuses people in a lot of ways. People say H is height, and then they get really confused with the negative height. Y is where you're located. Where do you all want to set 0 at? You can do wherever you want. You can do bottom or top. So you get to decide, but we'll say MGY initial. You have to define a 0 and you have to be consistent. Generally, people default to the ground being 0, and that's valid. You can totally do that. Totally works. All right. Any other energies you start with? So you start with potential energy. Any other types? Kinetic. Because you're moving. All right, 1/2 mv squared. Any springs involved in this problem? No springs. All right, great. Energy initial done. Is there any work being done? Is there any air resistance, friction, someone pushing or pulling it, anything outside the system that's affecting it? In this problem, we did not account for air resistance. We said no air resistance, so work is 0. Great. What energy do you end with? We end with kinetic and potential, MGY F plus 1/2 MV final F squared. Yeah, and I didn't give you the mass, but what do you find when you set up this equation? If every single term has mass in it, what happens to mass? It cancels. And what's really cool about this problem, y'all, is I gave you all this problem on I didn't give you maybe this exact problem. I could have given you all this problem on test 1. And how pleasant an experience is it when you have to break it into X and Y components? What would you all rather do? This equation ends up being just GY plus 1/2 V initial squared equals GY plus 1/2 VF squared. Plug stuff in and you're done. You could do projectile motion problems with conservation of energy. You don't care about components. And then here's something wild. If you do want to do components, you can. You just have to break up the terms into X and Y. And you can do energy in X and Y, as weird as that sounds. In that case, though, gravity does not affect the X. In that case, if you all do, you can do energy in X and Y. But you just got to, does gravity make things speed up in the X direction? No. If you all set up the X coordinate for this, it would just be 1/2 mv squared equals 1/2 mv squared. Ta-da! Initial velocity equals final velocity, whatever. I need to do examples of that. But great, this is so easy, y'all. This is so much easier than having to break things into components, find the Y component of velocity, find the time, then find the Y component of velocity, then use the time to find the X component. Well, the X component is constant at least, and then do the square root of VF squared X plus V Y squared. It's awful. It's much worse. Yeah.
So the question that you asked us earlier, would it be like work to say what it was?
So like if I added work to this? Yeah, so if I change this problem to a 1 kilogram ball, so I'd have to give you the mass, and if I had added air resistance, there would just be work done. You would just put that term there. If energy is lost, is work positive or negative? If air resistance, if I say I lose 3 joules of energy to air resistance, positive or negative? Negative. If you put in the equation that air resistance is a positive work, you are telling me that air resistance is adding energy to your system. Air resistance is making it go faster. That is not the case. If you all can just remember what work is, adding or losing energy, it's really easy to check your work on positives and negatives. Really, really, really easy. All right. Let's do a involved problem. So I actually have one already written on here. No air resistance, yes air resistance. Try it out. in the slides already. So if you just pull open the slides, what's cool, I guess if this is easier for you, this is kind of nice. I'm just going to send it to you as a clicker question. And now it's sent to all your screens. I didn't realize that. I guess I could have sent every single slide as a clicker question, which would have been a little silly. But at least it would have let you see it on my screen. If you came late, the projectors are down. That's why we're not doing it normal. It's not because I do like whiteboards, but they're suboptimal. Next semester, I just and I could yeah, I could. I'm gonna try this other one. This other one was hitting me about it. Yeah. Top hat. They all kind of do this. Yeah. One of the ones that Top Hat says they can do. We're gonna see how well they AI everything. Yeah. But supposedly it was trying to transform these conditions. I have no idea what the job is. But it'd be cool if we can do it. Because then I can make more clicker questions for people, more practice. And it also has a little thing that's a little AI with it. You can ask a question. I don't know. Is this something that yeah, that's okay. That's why I generally wait to take a solution. When I delete all the ink, so I don't actually remember the right answer. First step, draw a picture. If you can't draw a picture of what this looks like, the chances of you solving it correctly go down significantly. If you don't actually know what the heck is happening in your problem, you're going to have a very hard time. That's always the case. Every single problem you'll ever do in physics or engineering, you should visually imagine what's going on before you do anything. Because that lets you utilize your background knowledge, y'all. Pictures say 1,000 words to them. They tell you things that you might not be obvious, but when you draw a picture, it becomes very obvious. One day, if I haven't convinced you the value of drawing a picture, one day you'll believe me. Maybe it'll be years from now. Yeah, let me get you all the answers. Actually, that means I'm gonna have to do it because I don't think I put the answer on my even the worked out one. Yeah. This one's a clip. Yes. And then a little all right, I didn't write it out, so there's a very high chance I made a mistake, but I got 11.09. Because I did not write it out, there's a much higher chance I made a mistake than if I had written it out. But Angelina's solving it too, so that's my check. So that's where if the picture's off, the whole problem. Yeah. Yep. Subtle thing, but a critical thing. Woo! And I'll have you all know I've run your entire test through ChatGPT to make certain my answers were all correct. They are. I am double checking my work through the magic of ChatGPT as well. It is a tool. Back in the day, I'd have to find someone who was willing to solve my entire test for me. Yeah. I mean, people that know physics, it'll take them like 10 minutes. 10 to 15 minutes. At least for the multiple choice portion. I mean, that's one of those, when you get really good at something, you're going to do it really quickly. That's not an insult to you. That's going to happen with anything you all do in life. Like, look, let's take an extreme. Walking for y'all is really easy. You can get really far really quickly. My 5-month-old son can't get anywhere right now. So that's not like he can barely roll. It's an extreme example, but at the same time, yeah. I mean, I've been doing physics for 11 years. Like, it's not the age gap between you all and my kid is 18. Age gap between me and you all is 11. And the number of years I've been doing physics, and other people have been doing physics even longer. People doing physics longer than you all have been alive. And so, yeah, the fact that it takes them 15 minutes, you do something for 15, 20 years, it's not going to take you that long.
I also have to remind myself my foundation is horrible. So I'm like, when I'm like, why am I stuck at this? I'm like,
this is the first time. This is learning. You should never compare your performance to someone that's been doing it for many, many years. The best comparison is kind of the average individuals in this class. But even then, you have to recognize that everyone is also different here. And it's okay to be below the average in terms of how you're doing. Because you're better at other things. Like, that sounds like it's a hard thing to remember. It's a hard thing to remember, but at the end of the day, you just need to meet your own expectations.
yeah,
That's the whole problem.
it is. Save my life.
Right, I didn't know how to talk. You would be right.
She's so nice. I don't understand. She's so
By the gravitation. Nine is free force sport. So you're very blessed.
like, I'm a fantastic story.
The energy initials, we have equations.
You should all decide what's included in
Velocity, gravity, and we actually already have. We have the equations. So it is actually, but we kind of we derive something, and that is the potential energy stored in the spring. That is the work of the yeah, so work is anything like velocity, gravity, anything that involves one of those three camps. Yeah, by deriving the equation of the string, I guess you could do it. You could find the work of the string. You just would also do the work. Yeah. So that was the benefit. All right, if you're stumped, call me over. This is great opportunity for me to give you me or Leo or Angelina to give you individual pointers on how to proceed in this without giving you the entire thing. 11.09. If you got 11.09, you did it correctly. If you're having any challenges, call us over. Learning is best done when we don't give you the full solution, but we just give you the little nudge you need to get to the next step. That's effective learning. It makes your brain have to work a bunch, but that means you're learning. Learning's hard. It hurts your brain. First step, draw a picture. Taking any physics during the summer can be challenging. So it's very likely they will add more sections. I can't guarantee that, but it's very, very likely they're going to add more sections because it's in everyone's best interest. Physics during summer is very take the physics we did and then compress it. They don't reduce the content. So it's rough. It's a sink or swim. It can feel sink or swim during the summer. All right. So you draw a pretty picture, y'all. And if the picture's bad, your problem's bad. And someone already drew a picture over there. I forget. I think it was Leo. There's the picture, y'all.
Yeah, I wrote Delta X, but we're not
Nah, yeah, we're not solving for Delta X, but it's on there if you want it. It's a horizontal spring that pushes it off it, so that's my initial. We don't have the final. Where's the block end? Where's the final? Where's the block located? Super close to the ground. So draw another block near the ground and make it a different color or something. What type of it tells you in the title what type of problem this is, which is kind of unfortunate. What energies do I start with, y'all? Potential. What kind of potential? I have a spring potential. What's the equation for that? Yay. Is there any other energies in the beginning? I have a spring because there's a spring.
No.
Yeah.
Yes, you have to know.
What is the other type? You only got two other types. I'm telling you there's one more type. Is it moving in the beginning? No kinetic. Is it above ground?
Yes.
This is the checklist. Is there a spring being squished? Is it above ground?
Yes.
Is it moving?
No.
That's the checklist for the E energies. It's a checklist of 3 points. You just go through that checklist, and that's how you decide what energies are present. So yes, there's a spring being compressed, 1/2 kx squared. Yes, it's above ground, so mgy. No, it is not moving, so no kinetic. Is there anything else doing work on it? Is there any air resistance? Is there any pushing by anything other than a spring? Is there any friction? No. So is there any work? No. Plus 0 equals. What energy does it have at the end? Go through the checklist. Is it moving? So it has kinetic, 1/2 mv squared. Is it above ground? Is it above 0 at the end? No, it's at the ground at the end. Is there a spring being compressed at the end? No. So ta-da, you build your equation, you plug and chug. Conservation of energy is a build your own equation situation. If you can't build the equation, you cannot do anything with it. How do you get good at this? By doing examples and going through the checklist. All right. The next version. All right, I'm going to send this one out so you can see it. It's the exact same problem. However, It says how much work is being done by friction or air resistance if the final velocity is 2 meters per second. Try it. I'll put the answer up here in a sec. I'll tell you what the answer is in just a second once I solve it. What is different about this problem compared to the last one? That is the question. The answer is 595. And I'm not going to tell you whether it's positive or negative until a little bit. I don't want to spoil that. So what are our three options? And the spring and, yeah, there's two potentials. One spring, and then what's the other one? Yep. And it all comes from the equation. What's the equation? So how do you get kinetic energy based on that equation? What do you need to have? Exactly. I.e., if you have a velocity, you're moving. How do you get a spring energy? According to that equation, what variables show up? The distance of what particular? That is, it's the distance the spring is stretched or squished.
Okay, so like here, I would use the.
Yep.
Oh,
So, if there's no spring getting squished or stretched, x is 0.
okay.
And then this one, what do you need to have gravitational energy? You need to be somewhere that's not 0. You can be below 0. That's fine. You just can't be at 0.
Okay.
Yep. So that's the nice. If you just look at the equations, they tell you.
Okay.
Yep. Yeah. I was hoping. Yeah. 11.09. Yeah. This one's 595, I think. Yeah. What is work divided? What's the work definition? Work is if you gain energy, you gain joules. If you lost energy, you lost joules. Now in this case, positive or negative, work is
This is all the first one.
I really get excited to sit down and watch it.
So what's our definition of work?
Yeah.
The word definition.
Wait, this is 40.
You're gaining energy. You're losing energy. The weirdest part of work is just the word.
Right, it's a little janky, but I
Because it's called work.
questions that way.
But if you can just in your mind, anytime you use the word work, it should be
Like, modified by
and everything.
and then
Oh, of course.
like you and last time you actually like I wrote stuff down.
So this is air resistance.
That's and it if you write that
So that's friction. This is air resistance. What are we solving for in this problem?
I put my
Check the one I check the word.
No, literally all of you guys know that this is, I don't know, I'm like, just information load. I feel like I could just like, and then my grades.
I don't know. Sitting there intellectually.
There's no final indication, there's just
It's their fault.
I would just.
Yeah, I have no interest.
That's how you go through the equation.
Vitamins.
Initial plus work equals energy final. So where's the you don't need to go any farther. And that's always a problem. It's always important. What the heck am I even? What letter am I know? Otherwise, you might end up down a rabbit trail. In this case, yeah, and U would be the coefficient of friction, which is only relevant to certain slot surfaces. Yeah. And in which case, I'd say, what's the coefficient of friction? Yeah, does it work?
Yeah. The one I did.
Oh. Yeah, there's a few settings I have to set on it. Does it have the 50-minute?
And then it's also including.
I didn't update it. Okay. I'll fix it. I do it now, but it's streaming, so I can't.
Yeah.
I can't fix it right now. That was one of the things I meant to do. I got it all set up and I forgot to toggle a couple things. I made a new quiz for this one. Yeah, that one will get trashed.
I still.
So that's gonna be fun. Hopefully, no one else will start.
Yeah.
All right, this problem is exactly the same as the last problem. What is literally the only thing that's different in this problem? You have work. That's it. This problem is exactly the same. Energy initial plus work equals energy final. What energies do I have? In the beginning, I have spring and I have height. At the end, I have kinetic energy. But in this problem, there's actually work, and that's what we're solving for. Basically, anytime you all see a conservation of energy problem, this is usually the go-to. What if I asked you for the average force done? What is one extra step that you would have to do? How do you go from work to force? What's the relation between work and force? Yeah, work equals the integral of force times distance times cosine theta. This problem would be a nightmare to find that because the path you take is a parabolic, like I'd have to give you an equation for the path of the particle and that'd be disgusting. But I just want to remind you all, if I give you a conservation of energy problem and I say find force, that's something does. You have to relate work to force. Yeah. Yucky. Yeah. For this one, it's yucky. In general, I would only give you all one like this. If it was like going straight up and straight down, then that wouldn't be too bad because you can find the distance. Or if it's sliding on a surface. There's examples of those in the problem sets if you haven't seen them yet. All right. Another one. A 50-kilogram rock is sitting still. Suddenly it blows up into two pieces, one of which is 30 kilograms and has a velocity vector of 3i minus 7j. What is the magnitude of velocity of the other piece? You know what? Let's make this more interesting. What is the velocity vector of the other piece? The last one should be negative. Grab the square root too. Oh, real quick, the last problem was the work positive or negative? Why was it negative? Because you lost energy. The math reveals that to you. If you just do the math, you'll get a negative, and it makes sense. You lost energy. So. So bad.
What was the answer to the last question?
Everything over 2.
This one? Draw a picture. Decide what topic is being, write down your givens, decide what topic is being used here. Is it energy? Is it momentum? Is it universal gravity? Is it center of mass? Okay. Yeah.
Oh, I was doing reach. That's pretty tiny.
Yeah, it does.
That is a lot. What?
What's kind of our trigger?
Oh, plus 180.
That one has
113.
Wicked.
Let's try
Collisions for.
Yeah.
We have stuff. Yep. That's kind of the trigger that prevents this overheating. You guys receive things hitting each other or separated from each other. Religion is pretty much your only option.
I guess so that works.
They're vectors.
No, that's fun.
It's really rare.
Which is cool. The momentum of the whole system is still conserved. They are moving.
You know, we're like the.
But they'll move in opposite directions.
I know.
In some capacity.
So you know how you walk by every time?
And this is true of any collision.
Yes, right there. So I would like to.
Yeah, like a car that's parked in the car. Yeah, the car will start moving. The other car might, the original car might come to a rest. Because you know, if two cars hit each other head on, one's going to the right, one's on the left, they might stop. Why? Because they cancel each other. One had positive momentum, one had negative momentum. Okay, good. And you know the letter. I know. Just make your X and Y separate.
Yep. Dog fraud.
Yeah, I have no idea what the answer is.
Oh, the answer I got
Let's see what this answer is. And just to prove to you all, like writing it out, I'm going to write this out to figure out the answer because if I try to do it in my head, I will make a mistake, almost guaranteed. And so if you see me doing this, that's an indication that do not do stuff in your head. When there's this many steps involved, you will make a mistake eventually. If not now, you will eventually.
So you can actually do proportionality. That would be 30 volts. It would be 20
All right, so I got VF final equals negative 4.5 I hats plus 10.5 J hats. And pro tip, y'all, you have so much time on the test. When you all get an answer, check your work. Plug it back into the algebra and see if it works. It may seem like a waste of time, but I cannot remind you enough, you will make mistakes. And there are strategies to reduce mistakes, and one of those is checking your work. Either have someone else do it, check your work, or you yourself check your own work.
This was like early part of the year when his things in other classes.
Yeah.
Have you ever taken like chemistry or university?
All the masses. Yep. It was so what did you get? That was one of the hardest things you gotta draw. This is where it draws. Yeah. It's initially saying still, what does this velocity correspond to? The only person and the velocity of one Okay, if you're still solving this one, that's fine, but I'm going to kind of put the next problem up there. I only have like 2 more I want to throw at you all. I can definitely give you way more, but what we'll do is do 2 more problems, and then at that point, it'll be up to you if you want to stick around and ask me. We'll basically have class office hours where I stick around and help you all the problems if you want to stick around and solve stuff. Or you can do whatever. We'll do 1 or 2 more that I'm going to kind of throw at you all, and then after that, yeah. All right. A 500-kilogram car is traveling 30 meters per second. It runs into the wall. How does the force in a person compare if the time for the collision is 0.5 seconds, F1, compared to 2.5 seconds, F2? So basically, we have two scenarios. You got a car running into a wall. In one case, the time for the collision is 0.5 seconds. Find the force. In the other case, the time for the collision is 2.5 seconds. Find the force. How do those two forces compare? Two separate problems that we're comparing. So, can you all find the force? That's the question. Here you go. Yeah, I am so annoyed though that this work. It makes it so much harder to. What even happened? Like, there's a power outage. That's like, I mean, that's what it says on there, but I'm like, what happened? Everything turns on. It's a network issue, and I don't know anything about this. That's how I'm like, I can't say it's an easy fix or anything like that. But I also don't know.
Why was the network go out?
Yeah, that's basically my question. Of like, and how does that? How do we have a system that the power goes out and stops working? Like, if I turn off my computer and I turn it back on,
Things still work.
yeah, like what kind of system when it turns on doesn't just switch stuff up? I don't know. Again, that's me speaking.
Every time I got yeah, it was somewhere else.
The question more so is, anytime you equation, I'm saying wrong and I said right. Where did that relation come? That's how we're going to check it. You won't check it correctly. If you make up a happy one, I can say this divided by 25. Why? That's my question to you.
I'm gonna be honest. I'm not really sure. I'll just work on it.
Yeah, I was like
So that's the figure out why or why not. Why is that correct? Why and you can use some intuition. Which force should be bigger? The one in less time or the one in more time?
Why would it not be more time?
Okay, that sounds like I want you to. This is study. Yeah, that sounds like I want you to think through this because that's how studying is. Yep. So that's why you. Wait. Like if you do like 5, Did you find that's going to answer your question? Because you can make up any equation you want. The question is, why is it a valid equation?
No.
The question is,
Right on my notebook. I learned this
So the major thing here, I don't actually care about your answer. I care about, do you know how to get the answer, the process. Whenever you're studying, it's not about, can I solve this problem? It's about, do I know how to solve this type of problem? Do I know what relationships, what equations are relevant? When you're studying, that's the mindset. The right answer just tells you the right process. But you need to make sure you understand why that process is correct. That's the part that's key. Make through it. Big. I was like, see if you can. Can you find acceleration? That's right. Yep. Yep, you're doing the two components. Yep. Yeah. All right, y'all. Let's draw a picture. Let's draw a picture. What's this car doing in the beginning? Driving. It's moving. And it's going towards a wall. What's it doing at the end? Stopping. Great. We got a beautiful picture. What are my givens? Someone hook me up. What's given in this problem, y'all? A lot of y'all only wrote two givens. There's... Oh! Wait, all right. What? Nice. What's given? Hit me with it. There is 4 givens in this problem. Mass. Great. What else? 500 kilograms. Initial or final? What's my initial velocity is? 30. What's final velocity? 0. What else is given? Time. We got 2 different times that we're going to compare. What are we solving for? Force. Force equals question mark. We're going to compare the forces. So, there is many ways you could solve this. I could have given you all this problem in test 1 and you could solve it with kinematics. But there is another handy tool. What is the relationship between mass, velocity, force, and time? Momentum. What is the equation that relates momentum to force and velocity? There is an equation that says your change in momentum equals your force times your time. Impulse. How do their change in momentums compare? Does the momentum, so the change in momentums are the same in both cases. Their initial velocity and final velocity are the same. The initial velocity and final velocity are the same in both cases. So the change in momentum 1 equals F1 times 2 equals F2 times time 2. The change in momentum 1 equals the change in momentum 2. Therefore, F times T1, F1 T1 equals F2 T2. Basically, I didn't want you all to forget impulse. That's one of those things that kind of got tucked away and you might have forgotten about. But this is a very handy way to solve problems. This is one strategy, one tool. Don't forget about it. You can actually solve this with kinematics. You have the mass. You have the change in velocity. You have the time. You can find the acceleration. If you find the acceleration, you can find the force. Change in velocity over change in time is the acceleration. You can do this with kinematics and forces. All right. Long story short, the one with less time is a higher force. 5 times higher. 2.5 divided by, if you set it up, you get F1 times 0.5 equals F2 times 2.5. F1 equals 5 times F2. All right. I kind of want to do a center mass problem and then we'll call it good. Because I think that's the only one I haven't done one of. And then that'll be me covering one of everything. And then it's up to you to, if you want to stick around or whatever. I mean, at any point you all can leave today. Like none of the points of attendance or anything like that. But after this, I'll just kind of help you all with problem set problems if you so desire. Or whatever else you might have questions about. So let's see here. Center mass problem. An object is at 3i minus 2j. Where should, a 3 kilogram object is at 3i plus 2j. Where should I put give me a mass. 4 kilogram object. So that the center of mass is located at, give me a location, give me a number. 25. Oh, it's so big. Let's go with 2.5. I plus, give me a number. Between 1 and 10. You know, let's go with negative 1. 1's boring. Let's go with 7. All right. There you go. A 3 kilogram object is at 3i minus 2i, or 2j. Where should I put a 4 kilogram object so that the center of mass is shifted to 2.5i minus 7j? Draw a picture. Draw an XY coordinate system. That's what I'm doing. I'm just literally telling you to do what I'm doing. If it's good enough for me, it's probably good enough for you.
Yeah, so because V0 is 0, then it's 0, right? Because it's standing still. So this time, 0 times anything, right? Not always. When the velocity is 0. Yes. 50 times 0 is 0.
Yeah. But I miss all my classes.
That's why it's not like that. This equation is wrong.
What other classes?
I don't know why I know that on the second course, like for the x, because I had mass 1 times final velocity. 1 was 20. So I had 90 here plus 20.
You're checking it.
Oh, that seems crazy.
Terrible.
Damn. So I just messed something up. Oh, silly me. It's not 8.5. Forgot to do a step. And a reminder to you all, always, I forgot to mention to you all, does your answer make sense? You should always ask yourself that question. I just got some answers. I asked myself if it made sense, and I realized I made a mistake. Strategies to check yourself are some of the most useful strategies you can use. And drawing a picture will help you evaluate whether or not your answer makes sense. So, continue to mention it to you all because it's valuable. There we go. That's reasonable. And that is reasonable. Okay. The answer will pop up on the stream in 30 seconds or so. No, that was quick. I actually don't know how long the delay is on the stream. But it's ultra low latency. That's it? Wow, that's pretty good. I don't know. Probably future semesters. Wait, what are you doing? That's awesome.
Yeah, I'm dating him. He's like, he's a sibling.
Question. I think there's a question before that one. It's not like one before that. Do you know the answer?
Yeah, sometimes they can be converted.
Let me get my iPad because I have it on there.
You can do this, you can do center of mass. If not, it's great practice. It's great practice with people that can actually assist you in finding that next step and help you to learn it well.
It's like the right.
I think 0.5. Oh my god. It's good.
Yes.
This is me.
I mean, I know.
Yeah, because that's center mass equation. You put all things in
Yes. So, wait, the time period given to you. So, oh, this is two separate scenarios. It's not literally in one you're done with T 0.5, in another you're done with T 2.5. So you have two separate courses. So if you do everything right, you just want to compare. It's this was 0.5 or and I want you to compare how it's done. You got everything right. What you do is I messed up my F.
Don't worry, I messed up.
So you did everything right.
Good. I mean, that looks good, but you're dividing by 7. Why 7?
So it's like
Yeah, almost. Yeah.
Yeah, everything is on there.
No, so this is one side of the equation. What is it? Oh yeah, that's right. Oh, it's your eyes. Oh, I just don't get a choice. I mean, I guess I go back and forth. Okay, so I just played the yeah, I think your setup looks good. Yeah. When people's setup is really close to the right answer, it actually takes me a long time to figure out the error. Because they're way off.
The one literally 7 times.
Yeah, the math mistakes are really hard to actually find, and often I only find them by redoing the problem and having to go through it. If you came in late, want a note card, they're still up here. Grab one or don't.
That is the size limitation though for the test. Help me bring it in the whole shit.
I can't take that. Are you sure?
Oh wow.
Oh my god, why would you say that? You didn't know.
All right, and I'll just write out how to solve this so then I can close the stream. Because I got to fix something too. Remember, y'all, draw a picture. If you don't draw a picture, just make your life easier. I can't sell it enough. So we draw an XY coordinate system. 3 kilogram object is located a little bit below object 1. The center mass is 2.5 down 7. Which means we know object 2 is going to be somewhere way down there. You can predict where object 2 is going to be. Which lets you check your work. Which is nice. So yeah, we have mass 1 is 3 kilograms. We have R1 is 3I minus 2J. We have mass 2 is 4 kilograms. We're solving for R2. Oh, we have the center mass. R center mass is 2.5 I hat minus 7 J hat. 3 R center mass equals 1 over sum of the masses times each mass times where it's located. So 2.5 I hat minus 7 J hat. I'm going to need more room. Yeah.
Well, when I drew the picture, I don't feel like it really helped me too much.
What?
Did I do something?
Maybe. Let's see. Let me finish.
That's the right answer, but like, should I have used the picture?
The picture just lets you check your work. By looking at the picture, you can figure out that object 2 should be to the left of the center mass and way below it. But not like a crazy amount below it.
Should I draw my picture bed? So I drew 2 separate pictures. And like, this is for the 2 different.
Oh, yeah.
numbers.
So I drew one picture.
And you drew it on a coordinate plane?
Yeah.
And then what, you put like in between both points?
Yep. The center mass. Well, I put where the center mass is because we know.
Oh.
And then I'm like, where does object 2 need to be? And for the center mass to be there, you can logically, intuitively, probably kind of figure out that it's going to be that. So, yeah. All right. There you go. It's up there. I'll leave that there for a few seconds, and then I'll close the stream. Yeah, and I'll upload all this, so it'll be there. But yeah, if you got this, if you have any more questions,